Hi, everyone. Let's wrap up proton NMR spectroscopy. We're just going to tie up a few loose ends, talk about a few exceptions to some trends, and give you some help on solving hydrogen NMR spectra. Whoops, thought I was ready. I'm not. There you go. Get everything here, make this bigger. Okay, thanks, better. So more about splitting. And I thought, well, maybe if you're curious, you might want to look at an NMR spectrometer. So over here on the left, you can see the stairs that walk up to it. That gives you a sense of its size. Why is it so darn big? It's mainly so that we can create a super strong magnetic field. And to do that, you need a superconducting current, and the wires are only superconducting when they're cooled below liquid nitrogen temperature. So actually pretty close to liquid helium, which is that pretty close to absolute zero. It's getting pretty darn cold. Anyways, a little technology there, a little chemical engineering to make NMR spectroscopy possible. Okay, we're finishing up key concepts, Unit 4, Part 4. Sorry, I don't have the title here. It's right at the end of the document, just talking about some trends and some exceptions. So the big one here, splitting usually occurs when hydrogens are separated by 3 sigma bonds. That's the normal pattern. So if we have hydrogens on adjacent carbons, we say they're neighbors, they usually split each other. And if you count them, it's 1, 2, 3 sigma bonds that separate those hydrogens. And that usually counts as neighbors, right? However, nature, she makes the rules, so she's got a few exceptions. First one, kind of violates that pattern, is that if a hydrogen is involved in hydrogen bonding, now for us, that's going to be the alcohol groups, the amines, amides, carboxylic acids, those type of groups, OH and NH groups, they can hydrogen bond. Well, that hydrogen, when it's participating in hydrogen bonding, doesn't often split its neighbors, nor do its neighbors split that hydrogen. Okay, just this might help clarify it through an example. We have ethanol here, and there's the NMR spectrum of ethanol. How do you know? Well, take a look at the scale. It's around 10, and it's going backwards from 0 to the right. It increases. That's characteristic of, well, gosh, IR's down here. It starts on the right, increases to the left, but the scale goes up to 4,000. Carbon NMR also starts on the right, increases to the left, but it goes up to 200. Okay, so at a glance at the scale, the x-axis, you should be able to ascertain, is this IR, hydrogen NMR, or carbon NMR? And with the scale of 10, it's hydrogen. Okay, so what are we looking at? Well, we actually have the answer. It's ethanol, and it's got 6 hydrogens, but we don't see 6 peaks. There's only 3 peaks, meaning that we have some equivalent hydrogens. These 3 hydrogens all belong to 1 carbon. They're equivalent to each other. They're going to produce 1 peak. Or in other words, these 3 hydrogens make a peak. Each peak of those 3 just overlaps. They stack on top of themselves to make 1 peak. These 2 hydrogens are all attached to a carbon. They're equivalent to each other. These 2 H's are going to produce 1 peak. That's not a bond. And then there's a hydrogen and oxygen. This hydrogen still produces a peak. This is hydrogen NMR. All H's must produce peaks. Okay, and I know it's weird. The hydrogen's on an oxygen. It happens whenever you have an alcohol group or a carboxylic acid. Okay, so 6 hydrogens are supposed to give 6 peaks, but we have some equivalents here. This one's different from all the others. And so there's 1 type. Actually, let's label it this way. We usually label our peaks A, B, and C. And remember, on exams, you decide how you want to label them, 1, 2, 3, or CBA. Whatever you do, just make it clear, please. And then we want to assign these peaks to the hydrogens that produce those peaks. Well, which one's which? Well, normally we look at position, meaning farther downfield should be closer to the electronegative atom. So this hydrogen directly attached should be the farthest downfield, right? Nature, she makes the rules. Position can help us identify the hydrogens. The number of peaks, good, but there's also integration. And then finally splitting. Well, let's look at integration. Integration has to do with the area of each peak. The bigger the area, the more hydrogens that produce it. Okay, that's actually the most telling here, the most helpful. Which peak has the most area? C does. This cluster of peaks belong to one type of hydrogen, and it's the biggest, carries the most area. Therefore, it was made by the greatest number of hydrogens, these three. Which one's the second largest peak? Second largest peak in terms of area is peak A. The set of peaks has more area than this one, but not as much as this one. Yeah, peak A is being produced by those two hydrogens, leaving the smallest peak to the single hydrogen, which is not the farthest downfield. Okay, again, we warned you about that correlation table not being completely trustworthy. So here's a case where, yeah, the pattern, the tendency is farther downfield should be closer to more electronegative atoms or pi bonds. Not always, but integration is much more reliable. Also, the splitting pattern is quite reliable too. However, there's an exception here. Let's talk about peak C. Peak C, what is its splitting pattern? Well, I count 1, 2, 3 peaks. This is a triplet. This has been split into a triplet. So how many neighbors do the hydrogens that made peak C have? Remember that little catchy phrase, this is me and my neighbors. There's 3 peaks altogether, but if you call one of them me, the other 2 are the neighbors. Yeah, peak C, the hydrogens of peak C have 2 neighbors. So is that true? Hey, who made peak C? These 3 did. How many neighbors do you have? Well, they live in this house, go to the next door house next door, and there's 2 hydrogens living there. Yeah, there are 2 neighbors. Good. That's what we predict. Awesome. Let's go to peak A. Peak A is right here. And I count 1, 2, 3, 4 peaks. Now, some of you are saying, wait, I thought I could see more. So let's really zoom in here. We got a little weird thing happening because this data has been digitized, meaning the computer with its pixels have taken nice smooth peaks and pixelated it. Some of you are looking at this little bump right here, this shoulder, and saying, isn't that another peak? What about that one? Isn't that another peak? What about this? Isn't this a triplet? Because there's a little, no, it's not. Okay, so don't overanalyze like that. You need a gap between one peak and the next, right? So as you look at this peak right here, this peak goes all the way down the baseline before the next peak begins. So this little shoulder right there, just ignore it. That is not a peak. It's just a little glitch of the way this data was printed out on the screen. It's been pixelated. So the best thing to do is just to go to the top of the peaks and just kind of have a look. Just kind of say, okay, I see the top of the peak. It's right here. Here's the next top of the peak, top of the peak, top of the peak. There's 4. This is a quartet. And just leave it at that. All right. What does a quartet mean? How many neighbors do those hydrogens have? Well, the n+1 rule says n neighbors produce n+1 peaks, or you can do the me and my neighbors. But a quartet means you have 3 neighbors. 3 neighbors produce n+1, 3+1 neighbors, 4, a quartet. Okay, is that true? Go to A. Hey, A, how many neighbors do you have? And A, these 2 hydrogens say, well, if I look on this side, I see 3 neighbors. So yeah, the quartet's being split by 3 neighbors. But then you might say, wait, How come you're ignoring the other neighbor on the other side? I imagine hydrogen saying, oh yeah, that hydrogen, we never see him. He's off hydrogen bonding. Yeah, it turns out nature has decided that hydrogens that are off hydrogen bonding don't stick around to behave as neighbors. They're never home. They're hydrogen bonding, I guess. Anyways, this is a quartet, not a quintet. Meaning, properly speaking, you might say, hey, if I'm this hydrogen, I look to my left. If you're the hydrogen, that side's your left, I guess. Look to the other side. There's one H here, three H's. This should be 4, which means you have one more peak than at 5. Nature says, nope. For splitting, this is a hydrogen bonding hydrogen. Don't count it. And she didn't. Now, what about this hydrogen itself? You can look and say, hey, there are 2 hydrogens next door. 1, 2, 3 sigma bonds away. They should count as neighbors. Nope, not if it's off hydrogen bonding. We get a nice singlet here, which we would interpret to mean no neighbors. But in fact, when you draw the structure, it looks like it has neighbors. Hydrogen bonding doesn't give any splitting. Usually there's no splitting when you're off hydrogen bonding. Okay, well, how do you know for certain? Well, there's only 3 peaks here, and the integration really nails it down. There's 1H, 2H, 3 H's, producing a peak of 1, 2 height, 3, I'm sorry, area. This is a big medium-sized peak. This is the largest, more hydrogens here. But another idea is to go to the infrared spectrum. Infrared spectrum. And remember around 33, 3400, big, broad, strong peak, strong meaning far down, broad meaning wide, not a sharp peak like this one's nice and sharp. That indicates an alcohol group. It's like, wait, alcohols, they have hydrogen. So this hydrogen must show up in the NMR, and so it did. It's right here. And I had a student say, well, in the IR, this is big and broad. In NMR, it's kind of, I don't know about big, but it's kind of broad, meaning it's not split up into sharp peaks. It's going to be a singlet. No splitting when it's hydrogen bonding. That's an OH group, but where's my pen? There it is. The NH group can also hydrogen bond. So I found an example of that. I also found the IR. So the IR has got this crazy grid on it. It looks a little different than what we're accustomed to, but if you look down the x-axis, it says wave numbers, which are units for the infrared spectrum. Over here is kind of blurred, but it's 4,000, increasing to the left. Yep, this is infrared spectrum. What about 3,300-ish, 3,400? We got some broad peaks. They're not sharp. Look how sharp this is, meaning it's very narrow. These are wider, broader. This is not as strong. I mean, these peaks go a lot farther down. So that's how it suggests it's probably not an OH peak. It's probably an NH peak. Also, we have little spikes. I don't know if you call these spikes. They're more like peaks. And if you have a nice rounded peak, like I marked up over here, sorry, you can't even see it now. But if it's a nice rounded peak that comes down low, it usually means OH. And these that have spikes or peaks on them and not as intense, but still around 3,400, that suggests an NH. Oh, NH right there. Hydrogen bonding. That hydrogen is off hydrogen bonding, so we don't expect it to be split. And here's the hydrogen NMR spectrum, and there's a nice broad peak. A singlet not being split. Look how broad that is, just like this is broad. So they kind of match. And it's not like, hey, if it's broad like this, it means NH. No, the OH peaks can also be broad in the NMR too. But they're going to be singlets. NH, OH will be singlets. Sometimes they're kind of sharp like this one, but still a singlet. Sometimes they're broad like this one, still a singlet. Okay. Just be ready for that exception. If we see an amine or an alcohol in the hydrogen NMR, expect a broad peak. And the biggest clue is, do you have a peak at 3,400 in your infrared spectrum, the IR? It's like, okay, get ready to look for a broad singlet somewhere in the hydrogen NMR. Cool. Okay, that's the first kind of thing to look out for in this video about more about splitting. Here's a second one. I think we already covered this, but it doesn't hurt to reiterate. Equivalent hydrogens don't split each other, even if they're on adjacent carbons. So let's look at this hydrogen and that one. They're on adjacent carbons. Don't they behave as neighbors? Nature says no. Here is the NMR spectrum for cyclohexane, a clean singlet. There are no neighbors, no splitting. But wait, doesn't this hydrogen have neighbors on it over here and over there? Don't they all have neighbors? Well, nature says that, hey, if they're equivalent, they're not neighbors, they're family. They live in next door houses, but they're all family. They don't count as neighbors, therefore they don't split each other. Yeah, does that work? I'm not going to find family hydrogens in any textbook, but it's a way to remember it. They're equivalent. They're just living in separate houses. They're family. They're not neighbors. They don't split each other. Yeah, okay. If they're equivalent, we sometimes say there's a plane of symmetry, right? So you could, so for focus on these hydrogens here, hey, how come they don't split each other? Well, because the molecule's symmetrical. These hydrogens are equivalent to those hydrogens, column A. And then you might say, based on this line, these hydrogens should be equivalent to each other, and then these hydrogens should be equivalent to each other. Aren't there three types? And so I'll say nope, because there's another plane symmetry here, meaning that now across this line, A is equivalent to B. So let's not call it B, let's call it A now. And then B is equivalent to C. Well, no, let's call it B now, because they're the same. What else? We got A equivalent to C. Well, no, that's not C, that's A now. And maybe I should have said, instead of renaming this one, this is, C was here. Well, now A is equivalent to C. So what was C is now A. And A is equivalent to B. So what was B is now A. Hey, everybody is peak A. And that's all we got. I don't know, does that help? I feel like I really messed that up. You can cut it into 3 different symmetry planes where everybody's equivalent to everybody else. There are no neighbors, they're all equivalent. You only get one peak. Equivalent hydrogens, even if they're on adjacent carbons, if they're equivalent, they don't split each other. Okay, 2 more things to worry about, to be aware of, not worry. Okay, this one's interesting. I do not intend to put this on your exams. However, if you go into the lab and collect your own NMR data, this could show up. So let's take a look. This is pi bonds that can allow for long-range splitting. Now, what do I mean by that? Well, normally hydrogens have to be on adjacent, that should not be a C, should be on adjacent carbons in order to split each other. They need to be separated by 3 sigma bonds. Well, it turns out that if you have a pi bond in the system along the way, that sometimes you can get distance neighbors to detect each other. So 1, 2, 3, 4 pi bonds normally should be too far away, but if along one of those sigma bonds there's a pi bond, you can sometimes get long-range splitting, meaning, hey, they behave like neighbors even though they're farther than being on adjacent carbons. It's usually 4 sigma bonds. If at least 1 pi bond is found among those 4 pi bonds, 4 sigma bonds. Kind of think like this pi bond is like an antenna or an amplifier. It's amplifying the signal so they can see each other. And what does that look like? Well, here's an example. We got this molecule here. I'm sure I'm going to mark it up. So when I redraw it, so I can mark up this one. And actually, I will put in the hydrogens. Okay. And this one is A, this one is B, and this one is C, and they've already been identified. Nice. Oh, here's a full zoomed out view of the NMR spectrum. And you can see it's hard to determine what the splitting pattern is. I mean, at a glance, I would assume these are all singlets. Not until you zoom in do you actually see, oh, wow, this is a very narrow, not well split doublet. And what the heck is this? So we'll skip that. Let's go over here to C. C is definitely a doublet because these are cleanly separated. That's how a doublet is supposed to be. The middle does not completely go back down to the baseline. It's not a clean doublet, but you can tell there are two peaks. So that's kind of like a narrow doublet. I don't know what you want to call it. But look at the distance between these peaks. Scientists call that a coupling constant. You can go down to the x-axis and actually measure how many ppm one peak is separated from the other. You can measure that. And you can actually, but just at a glance, you can see that the distance between these peaks is much smaller than the distance between these two peaks, right? Scientists will call this the coupling constant between the peaks of peak C. That'll be larger. I don't know, I should probably just guesstimate it. Looks like I got one peak right here at 7.9. 7.59, sorry. And then we got this center of the peak. Yeah, what is that? 7.63. So it looks like the coupling constant is about 0.04, something like that. Something like that. And this one, gosh, it's so close. Why don't we just call it the coupling constant between the peaks of A? And I don't remember the exact notation. I don't think it's A, but we'll just use that for now. Sorry for those of you who have taken more advanced courses. I don't remember the actual notation here, but let's just say that's about 0.1 ppm apart. Cool. All righty. You can now have numbers. These is a bigger number. Okay, now let's go back and figure out what B is doing here. Well, look at the distance between this peak and that peak. Isn't the same as this one? Sure looks like it. And between this peak and that peak, that's the same too. Now look at the tallest peaks. So I'm looking at this one and this one. Wait, that distance, that coupling constant, doesn't look like to be the same between these two. It actually is. So what is happening here? Well, for peak B, one hydrogen is splitting into a doublet, and the second hydrogen is splitting those doublets into more doublets. Let's break it down a little bit. Hey, B, what's happening with you? Well, I definitely have a neighbor right here. I go 1, 2, 3 sigma bonds, and there's a hydrogen next door. Go 1, 2, 3 sigma bonds, there's no hydrogen here. Hydrogen labeled with a B has one neighbor. And if you have one neighbor, the peak should be split into a doublet by peak C. But if we look at A and we count 1 sigma, 2 sigma, 3 sigma, 4 sigma bonds, and there's a pi bond intervening, now B can see A through long distance. The coupling constant is going to be weak. It's only going to be this far apart. But B feels like it has a distant neighbor over here. It has one distant neighbor. And if you have one neighbor, you're split into a doublet. So what A does is it takes the doublet that already was formed from C and splits it again, splits this into a narrow doublet and splits the other one into a narrow doublet. And we get this pair of doublets, a doublet, if you will. Okay, let me reiterate. I'm not going to intentionally put this phenomenon on your exams. But in the lab, this can be useful. Because if you see this double of doublets, that tells you, hey, there's a distant neighbor. Go find another peak that's split by the same amount, and there's your distant neighbor. So this distance matches that distance. You know, the separation gap there, the width, they match. That identifies those neighbors. And if you compare this to that width, that matches this one. Hey, these are neighbors. Cool. Nice. All righty. So long distance splitting because of a pi bond. Oh yeah. And then here's something else. You might have noticed that theoretically, when we talked about the theory behind splitting, we said, hey, you get a nice doublet. And I drew my peaks so they had the same height. Theoretically, that's supposed to happen. Well, experimentally, the real data, that doesn't always happen. So here's a quartet, and I would expect the outer peaks to be the same height, and the two inner ones should be taller, but the two of them together, comparing one to the other, should be the same height, but they're not. This one here is a little bit taller. And if you do this one on the right is a little bit taller. And if you come over here, the same deal. This one and that one are not the same height. That's what I would expect. This is called roofing, or what is this else is called? I forget the other word for it. But it's a little phenomenon, I think it's second order coupling, where instead of being nice and symmetrical peaks, they'll be a little bit tilted, and they tilt or lean towards their neighbor. So it turns out these, peak A, if you will, and peak B of a brand new molecule, there's a certain number of hydrogens that are producing this peak, and then they are being split into a quartet. Okay, so how many neighbors does peak A have? Well, a quartet is n+1. Number of neighbors must be 3. Or you can say me and my neighbors, 1, 2, 3. Okay, and then this slanting or this tilting is actually saying, hey, the 3 neighbors are somewhere over there. Well, I'll come over to B. B is another set of hydrogens, and they have some neighbors because the neighbors have split them into a triplet. How many neighbors do the triplet have? Do hydrogens that produce peak B have? They have 2 neighbors. And this tilting says, hey, go look for the 2 neighbors over there. So it turns out there must be 2 hydrogens producing peak A and 3 hydrogens producing peak B. And this tilting helps you identify them and match them up. Let's just check. Is that working over here? Yeah, so look at C. C is tilting. Well, that doesn't help. There's 2 peaks over here. They're all over here on the left side. C, of course, you can be pointing that way. And so is A. A is pointing that way. But if you can zoom in, I can zoom in. Take a look at B. So the little peak splitting here, oh, I marked it all up, but you can see how this is pointing to the left, saying, hey, the little neighbor, the long distance neighbor is actually A. And then B, this peak is higher, it's going that way. B, the bigger gap is saying, hey, go look to the right to find the neighbor. And there it is, peak C, the hydrogens that produce peak C. Cool. So that's a phenomenon that you can use to your advantage on the exam. This roofing effect, the second order coupling effect, they kind of point to their neighbors. Nice. Okay, that was a third of the notes I want to make about exceptions to splitting and stuff. Here's the last one. Actually, we kind of saw this already. Usually hydrogens attached to the same carbon are equivalent, and therefore they don't count as neighbors, and they don't split each other. There's an exception, the alkene, which I have a little farther down. So just to reiterate here, we got this ether, dipropyl ether, it turns out. There's a propyl group on the left, propyl group on the right. There's a nice clean symmetry down the middle. So these hydrogens are equivalent to that hydrogen. This top one is equivalent to that one because they're attached to the same carbon. There's also a big plane of symmetry running horizontally here too, that helps. But more to the fact that these 2 H's are attached to the same carbon, that helps make them equivalent. This hydrogen labeled the B, symmetry, they're equivalent to these. This one's equivalent to that one because they're attached to the same carbon, and so forth. Yeah, cool. So if you look at peak B, how many neighbors do you have? Well, there's 2 neighbors over here, and there's 3 neighbors over there, a total of 5 neighbors. So we should get how many peaks? 5 neighbors should make n plus 1, 6 peaks. 1, 2, 3, 4, 5, 6. Yep. And they're kind of level, although this one does point this way. Peak A is pointing to the left. Peak C is kind of pointing to the right. There you go. They're pointing at at their neighbors. Anyways, the point here is, hey, we have some equivalent hydrogens. They don't split each other, right? You don't say, hey, hydrogen, how many neighbors do you have? Well, you're supposed to say, go next door to this carbon, see 2 hydrogens. You don't say, oh, this is my neighbor and 1 more and 3 altogether. No, no, no. This hydrogen's living in the same house as this one. Attached same carbon, should be equivalent. Doesn't count as a neighbor. They don't split each other. Okay, that's the normal way to do it. The big exception, and there are others, but you won't see them in this class. Think in the homework, there's one of these. The big exception are the alkenes, carbon-carbon double bonds. What's making those hydrogens non-equivalent, meaning they can split each other now, is that you don't get rotation about a double bond. So as you look at this molecule, this alkene, and you ask, okay, we got a big ester group over here, pi bonds, electronegative oxygens, that's going to send the signal in the NMR downfield to the left. So who's closest? Well, I would have thought B was the closest. But it turns out hydrogen A is the farthest downfield. So here's 0, where TMS is, the most shielded molecule. It's way upfield. And as you get close to oxygen, you should be shifting downfield. Well, it turns out A is through space. If you measure it, they're closer. Although I would argue that would have been closer. But hey, I don't make the rules. Nature does. And wait, it's being split into a doublet. Well, peak A does have a neighbor over here. That's cool. But what about B? Hey B, what's going on with you? Why do you have this funky? Looks like you have a doublet of doublets, and it does. So B says, well, I have one neighbor that's cis to myself, and I have another neighbor that's trans. And these two, A and B, are not equivalent to each other. So they're actually starting to split each other. So if we go down here, and we got peak A, so hydrogen A, you're being split into a doublet. But then, if we could zoom in more, it turns out there is a tiny little doublet here and a tiny little doublet there produced by this neighbor. Wait, you live in the same house. I know, it's the exception. So to reemphasize, I don't intend to put, I'll just go even stronger. I will not put an alkene on the hydrogen NMR problem. There's one in the homework, I believe, just so you see it. And for the future chem majors who may encounter this, at least you've been exposed to the idea. Okay, probably said way too much. We don't have to overanalyze this. I just want to mention for those chem majors, these are called little, what do they call this? Splitting trees? I forget what they call it. But it's a way to analyze the data. So what's going on here? Oh, and there's the J coupling constant notation. Awesome. Let's talk about what the peak from hydrogen B is doing. Hydrogen B is right here. What's going on with you? Well, first, the neighbor that's trans, this hydrogen, is splitting it into a nice clean doublet. So it splits the original peak into a doublet. And the coupling constant, the distance, is the distance JAB. That makes sense. The coupling constant corresponding to the neighbors A and B. And then each of those peaks is being split again by this neighbor, neighbor C. Its coupling constant is smaller. It's labeled J, the coupling constant between B and C. And it happens to be the cis hydrogens. There you go. So that's the notation. Interesting, but again, it's not going to appear on your exams. But if you see something goofy at around 6 on the NMR scale. If you go to the correlation table, that says where the alkenes are. So peaks around 6 are either, well, commonly are benzene rings or alkenes, hydrogens on those groups. And if you see some funky splitting pattern, you might say, ooh, this looks like the alkene functional group. You might come here, review this video, because it's not going to be on the exam. It might be in the homework. And I think that's everything. Cool. We'll leave it with this image up, the more common case. And I'll see you in the next video.